Hello everyone and welcome to our latest webinar where we're going to be concentrating on packaging, and that is on mainly kegging and canning. So what we're going to do is just see how many people have come in. And then, yeah, we will get going. So, yeah, today we are going to concentrate on packaging. So we've been through pretty much all the process now, and this will wrap up all the rest of what we've done. So we're going to start thinking about actually what we need to achieve when we put beer into package. So we want it to hold the beer without getting any leaks or leaking anywhere. And then we want to make sure that we protect the customer from any harm with it as well. We don't want it exploding in the hands or anything like that, or in the car when they're driving home and getting the car full of beer. We also want the package to make sure that it's got its shelf life, and it manages to keep its shelf life, so the beer stays in the best possible quality all the way through. And it also needs to hold the right volume. So if we're selling a 330ml can, we need it to actually hold 330ml. We want it to make sure there's no dispense issues. So again, it needs to make sure that it can the pressure's right whenever we're fitting up to a keg fitting, and again the pressure within the can when we're opening it, we don't want it to fob over everywhere when it opens. And we also need to make sure it's easy to transport and store. There's no point in having a package that takes up a load of room storage wise and a load of pallet space when we're storing it, when we're moving it around. Okay, so the first thing we need to think about when we come to packaging beer is actually what the condition the beer's in, and we need to make sure that that's right for package, because it's going to have effects. So clarity wise, the beer can be hazy or unhazy. It's obviously up to how you want to present the beer to the customer, but if it's got yeast in it, you do want the yeast cells to be below 1 million cells per mil. Too much yeast cells, it's really not nice for the customer, and as well you might encourage some secondary fermentation in there as well, and that might become a bit of an issue. We need to make sure the temperature is well regulated. Anything above 4 degrees C, you're not going to be able to get the CO2 in solution, and it's also going to fob quite a bit when you're filling, so you're going to struggle to get the actual right quantity of beer into pack. If we are diluting any beer, it happens in some of the packaging plants, contract packers, or in the bigger brewers. You really want it to be done before pack, and you want it to go on a go no go. As you're diluting the beer, you are changing the whole structure of the beer, so it can have an effect on the PG and the palate, so and the pH as well. So yeah, it needs to be well checked. And as well, if you're using any water for dilution, you do need to make sure there's no chlorine in it, because you can get some chlorophenolic flavors coming through. You need to make sure that there's good top pressure on the tank to make sure that the gas stays within solution. If the incorrect top pressures on the tank, as you're pumping it out, you're going to get either a gas pickup if there's too much, or you're going to lose some gas if there's not enough top pressure on there. And also you do run the risk of sucking the tank in as well, which is pretty catastrophic. And as well, if there's not the right amount on there, then you can force the pump to cavitate, where it kind of rushes, and speeds up, slows down, and again, that's not great. You're going to pick up temperature and also DO2 as well. Before you do package it, check the DO2 and the CO2 levels, and do check a spec. Do have a spec for them and keep them as tight as what you can. And ensure the lines is purged properly as well with water. So you need to think about what you're going to be packaging on what days. It's not great practice to follow out a stout by a lager, because you're going to get colour and flavour pick up. So do make sure that the line's thoroughly flushed out properly before you present it with new beer. For measuring CO2, there's a couple of ways that we do it. The traditional method has been thermal conductivity. So we've got the Corning 965, which isn't really produced anymore, but there's still a lot out there in use, and Olympiatic services will still come and service them and fix them for you. And we've also got the Orbis 3658. So with the Corning, we get a sample jar that's got a little bit of caustic in the bottom. We run the CO2 into the caustic, and that binds the CO2. Sorry, we run the beer into the caustic, and that basically binds the CO2. And then we inject it into the machine, and we'll get a CO2 reading from that. With the Orbisphere, which again, I think they're stopped use now, it runs a bit like what a DO2 meter does, but the liquid flows over a thermal conductivity sensor, and it'll give you a CO2 reading. The ones that we see more and more of these days are the pressure temperature variety. Now, pressure temperature has been around for a very long time, but it does, when it's working out the CO2, it uses, if there's any air in there, the air will basically adjust the sample. So any nitrogen in there, any oxygen in there could have an effect on the sample. So the Anton Power ones have basically come up with this multiple volume expansion, which basically allows the nitrogen or the air within any samples to not affect the CO2 reading. So you can actually get a nitrogen reading and a CO2 reading from those. CO2 is measured in either grams per litre or volumes, and one volume is 1.967 grams per litre. So why should we measure it? And just to make sure it's right, well, one of the biggest ones is product safety. If we do overcarbonate going into can or keg even, it can really have some safety fears as you're opening the can, beer fobbing over everywhere. If it's actually going into bottle, it could burst the bottle. Controlling the product flavour as well. CO2 really does lift the beer. So having different levels of CO2 is obviously going to affect how it tastes. Same thing with consistency. A couple of different levels of CO2s and a few different batches really does change the flavour of the beer. And cost as well, because it's pretty expensive, CO2. There's a bit of a difference as well between how much gas will go between the different packages that we use as well. So we've got a little bit of a table here where if we've got a lager for keg, we're probably going to be aiming for around about 2.45 volumes, whereas in can we may be up at one volume higher at 2.55, and that pretty much goes the same all the way through. You'll generally get a higher CO2 level in can than what you will do in keg. DO2 measurements come on a long way in the last few years. So the older fashioned way was using an electromechanical sensor where you've got a probe, and again the beer will flow over it and it will measure the oxygen within the liquid as it flows through it. And you've also got the optical sensors now as well, where it'll basically fire an LED light and depending on the oxygen levels within the beer, some of the light will be absorbed and will give you a reading of how much O2 is in the beer. With them all, it's really important to keep them clean, because you've got any biogrowth in there, it will use oxygen, it will skew the reading. The optical ones are a lot easier to keep clean and really keep them in use. The electromechanical ones need quite a bit of tender loving care to make sure that the membranes don't fail in any way and don't get bubbles below them. But the optical ones these days are very, very good. When we are using them, we need to make sure that there is good flow control. So do take a look at the recommendations from the supplier to make sure that you're within the right control going through. If you just turn off the flow and don't let it go, you'll get an incorrect reading, generally low. Also need to keep an eye on what hose material we use. You do see some silicone hoses knocking about, and silicone basically allows oxygen to get in. So again, that can skew your your results. And you want to make sure there's no leaks. If you've got a leak from any of your fittings anywhere, then again, you can get incorrect readings from that. And if we're sampling small packs or cans, we might need a sampling device as well, which is basically a piercing unit that will put a tube into the can, and then it'll put nitrogen top pressure onto it, and then force a sample through the DO2 meter. And then that allows us to measure the total in package oxygen. So we really want to control DO2. Everybody knows what effect it has on beer. So there's quite a few ways we can do this. We can use deaerated water to flush out all the lines and the tanks, and then purge it with CO2. So if you fill it with deaerated liquor, it's fine to just then follow beer through. It'll take most of the oxygen out. If you've not got deaerated liquor, then if you fill your lines with water and then blow it out with CO2 or nitrogen, that'll really bring the CO2 levels down. And the same with tanks as well. If you really want to make sure there's no oxygen in the tank, you fill them with water, put top pressure on, and then blow the water out, and they'll be fully redoxed. Making sure the system's fully balanced, again, to stop pump cavitation. So you can do that by using a VSD, which is a variable speed drive. So it's really good when you fill in a tank to start slow, start really, really slow until you build up enough volume within the tank where the liquid's going into the liquid, and then you can speed up and then slow it down again at the end once your feed tanks becoming empty, which is really easy to do with VSD. As well, if you've got a flow level indicator on there, as soon as the tank, the feed tank's empty, it'll shut off, and you won't start pulling through any air that could be in the tank. In some bigger breweries, it's quite normal to package from a few different tanks during the day. So as you are changing over from the empty tank onto the new tank, it's a really easy way to then pick up oxygen levels as you're doing it. So that's really something to keep an eye on. It's generally good practice to connect them all up at the start and purge through. The fill level within the pack's really critical as well. So if you've not got beer within, you've got obviously your beer volume, then you've got the headspace. The lower, the less beer that you've got in there, and the greater the headspace, the greater the oxygen you're going to get within that pack. So I think if you've got a variation of 2 milliliters within your pack, that can actually be an increase of 40 parts per billion of oxygen within the actual TPO of the beer. It's really good to walk the route as well, not just to make sure you've got the right tank connected up, or somebody from the other shift hasn't gone over and disconnected it, but to check for leaks. if you've got a leak anywhere on the pumps, on any fittings, then you're going to start sucking oxygen into the system. And any seals, RJTs especially, they get quite hard after the year, so it's really good to swap them all over and keep everything fresh. Make sure that when you're using hoses, you do look at them before. Just give them a good inspection before use. So look down the hose. When you connect it on to the tank or the flow plate where the collar is, it'll be okay, and then it generally starts to bend after that, and that bend, that crease, that's where the hose is gonna generally wear. So have a look to make sure the hose is intact, and give it a smell as well to make sure that it's fit for beer. And keep an eye on them for the year. Your hose manufacturer will generally do a hose register for you, and they'll also do a pressure check to make sure that that they're going to be able to withstand the pressure that they're under, especially under the CIP. And it's always good to get the proper sways ends as well, rather than the Jubilee clips. Pumps are obviously a major risk of picking up any oxygen. So keep an eye on the pumps, service them regularly, and again, listen out for any sign of that cavitation. So coming on to total package oxygen. So as said before, we've got the beer, and then we've got the headspace. So the total package oxygen is the combination of the beer within the oxygen within the beer and then the headspace. It's not basically shaking it up and then running it through the DO meter and then getting your results. That is the oxygen within the beer, and you need that, but we need to worry about a few bits and bobs as well. So we need to make sure that we've got equilibrium. So we're doing that by shaking the package. That makes sure that any of the oxygen within the headspace is evenly distributed between the beer and then the headspace when it settles out. We need to know the dissolved oxygen then of that liquid, which we get when we measure it. We need to know the temperature as well, because the temperature has different effects on how much oxygen's within the liquid and the headspace. We need to know the right empty weight of the package, and if we know the right empty weight, then we can measure the package to find out the brimful volume and also the actual volume, and then we can use that to make sure we've got the actual volume of headspace. And then from that, there's lots of calculators that you can use. I found one at the link just down there on the Master Brewers Association of America. You can put all of that into an Excel spreadsheet and it will spit out your TPO for that particular sample. And generally, it's around about 3 times higher than what you would normally measure from your dissolved oxygen meter. It's really, really important as well to check each head, because you just never know. You may just set one and think, yeah, everything's fine, but make sure you check each head, because you might find a problem on one particular head. So something else that we might want to do is stabilize the beer, so biologically stabilize it. So whether that's hazy beer or filtered bright beer, we might want to stabilize it. So that will basically make sure that there's no microorganisms within that package that's going to spoil it over its shelf life. So we can do that by 2 methods. We can either do it by pasteurization, which will inactivate anything that's in there, or we can do it by filtration, which will remove it. Obviously, if we're filtering it, it's got to be bright beer. So if we're pasteurizing it is it's a statistical kill rate of microorganisms. So it's basically looking at what microorganism is in there and what temperature and what time is needed to deactivate it. It's the thermal stabilization of beer using it. So basically we heat it up, and it can happen either before packaging in a flash pasteurizer or after packaging in a tunnel pasteurizer. It inactivates any microorganisms, so they're not capable of growing, and also inactivates any enzymes, so you're not going to get unwanted chemical changes like what you might get from any biotransformation. But it's not sterilization. What it does, because we are heating up the products, it does have an impact, and we measure the thermal impact. So we measure this in thermal impact units. So basically, at every 10-degree rise in temperature, any reactions will double. So by heating up the beer, any reactions that are going to happen twice as fast. So if we do have any oxygen within there, and we pasteurize it, then we're really going to oxidize it very, very quickly. So to make sure we do get effective pasteurization, there's a few things we think about. So one is the actual time of what we're going to pasteurize. One's the temperature. What's actually present in the beer micro-wise. So different bacteria will have different temperatures and times that's needed to deactivate them. Again, the concentration, so the more microorganisms that's in there, the more stabilization it's going to need, and also the chemical composition of the beer. So if you've got a big thick stout, it's going to need a little bit more heat treatments than a really light lager, just because there's a bit more viscosity to the beer and the heat won't pass quite so easily. And we can see from the table below, we've got a couple of the different microorganisms within beer to get deactivated at different pasteurization units. So what is a pasteurization unit? It's basically one PU is beer that's been held for 1 minute at 60 degrees C, and it's Louis Pasteur who did the research work on this. So we've got a calculation that we can use for this, and it's basically a PU equals the holding time in minutes times by 0.1393 to the power of the holding temperature minus 60. So we put all that together, we'll get the PU of what we need. And typical PUs that you'll come across in the UK and Europe is between 20 and 30. And then USA, Japan is generally a bit lower at 5 to 15. And that's historically between the beers that was brewed between the different places. So in the US, Japan, you'll get quite light lagers. And then in the UK and Europe, you've got a bit of a different array of beers, giving it different UK bitters or different kind of beers from Germany, some wheat beers. So, have we missed one there? Nope. So if we look at the graph below, we can see that as the temperature increases, the pasteurization also increases very rapidly. So if we hold a beer for 20 minutes at 6 degrees C, we're going to get 20 PUs. But if we increase that to 67 degrees C, for the same amount of PUs, we'll need to hold it for 2 minutes. And then again to 74 degrees C, we'll need to hold it for 12 seconds to get the same 20 pasteurization units. And from the two ways of pasteurizing, the tunnel pasteurizers take longer at lower temperatures because the whole package is being heated. So you've got to get through the cans or the walls, and you've got to get the heat through that. And then flash pasteurizers, because you're just basically heating the beer up, have a lot shorter times at higher temperatures. With tunnel pasteurizers, as I said, the beer is pasteurized within the container, and they are actually quite simple bits of kit for as complex of what they are. All that they are is a series of water tanks heated water tanks or cool water tanks that sprays water over the beer as it passes through. As the product moves through, so it enters the pasteurizer, it's either going to get picked up on a walking beam or just on a conveyor, and it basically gets water sprayed on it. But we can't just go straight away for pasteurizing temperature because we don't want to put too much shock onto the products because we might damage the container. So we start off slowly, and then we gradually increase the temperature and then cool it down at the end. A lot of pasteurizers these days as well have got PU control on them. So if they do sense that the PU within the package is going to go high for some reason, say that there's a stoppage at the labeler or the packer or anything, they'll basically put cold water on and they'll quench everything that's in there and stop the pasteurizing. As well as that, we also use thermographs, and we'll put them through different parts of the pasteurizer as it's going through, just to double check. So red post will be a prime example where it will basically measure the temperature as it's passing through the tunnel, and it'll give you a nice graph of exactly what's happening. And a way of saving water with these with a tunnel pasteurizer is, as the bottles obviously or the cans go in really cold, and then that water that flows on top of it, the warm water that flows on top of it gets cooled down. We'll then pump that around and we'll probably put it on for the pre-cooled section just as it's out pasteurizing. And then we've got cooler water that then warms up from the warmer bottles in the packaging, and then they'll go back to the preheat. So we'll regenerate water that way to save as much energy as we can. So flash pasteurizers pasteurize the beer, not just all, doesn't do anything with the package, it's just the beer, and it's all pre-filter, obviously. Generally used in conjunction with a sterile buffer tank because you really need to make sure you've got good flow control on these, and they're a lot higher temperatures. So whereas the buffer tank is going to be, whereas the tunnel pasteurizer is going to be around 60 degrees, the flash pasteurizers are more up at 72 for that 12 seconds. Now, because you think that we're going higher in temperature, you think that we're going to have more of a thermal impact within the beer, but it's actually a lot less because it's a really short time where it's heated. So with a tunnel pasteurizer, again, it's going to be over 20 degrees for around about an hour, whereas the flash pasteurizers, within a minute, it's up and back down again. So really, really good for the beer. You do need to look after them though and make sure that they're managed right with strict cleaning and sterilization regime, and they run at particularly high pressure because as we warm the beer up with the CO2 in it, the CO2 wants to break out the solution. So typically run around about 9 or 8 or 9 bar. You really, if that CO2 comes out of solution, then we're going to get little pockets of bubbles in there, and we're not going to get good heat transfer, and we're not going to pasteurize properly. And they're generally coming in 4 sections where the beer comes in, gets heated up, it then gets a preheat, heated to pasteurization temperature, goes through the holding cell, and then gets cooled back down again. The other way that we've got is by sterile filtration, which instead of leaving organisms within the beer and killing them by heat, strips them out. So we're basically filtering them out. So with these, you don't get any damage from any heat treatments. Again, it's before the package. So the differences between it being before and after packages, if it's before, you've still got quite a lot that can go wrong with when you're filling, up until you put the cap on for any kind of contamination to take place. Whereas if you put it through a tunnel pasteurizer, it makes you sleep properly at night if you're a packaging manager, because you know that if anything's happened as it goes into the container, it's still pretty much going to be sorted. So the sterile filters, the way that we look at how they work is basically the load reduction from what's going into the filter to what's coming out. And how much is being taken out is basically how we see how effective they are. So you can see it removes a very high percentage of organisms, but we can look at it from a slightly different way as well and go to the log reduction value. And we can see that if you're going for a filter, you want the log reduction value to be less than 12. There's also two different ways that filters are rated. So the difference is the description of what the filters are. Seems quite simple, really. So with the nominal, it's an arbitration micron value assigned by the filter manufacturer. So there's a lot of ambiguity there, and it's not set in stone of exactly what happens. With an absolute, it's the diameter of the largest hard spherical particle that will pass through under a specified test condition. So that's a lot more straight bat. Now, as a result of that, with thinking about what's at the start to what's at the end, if you've got an absolute filter next to a nominal filter in the same line with the same beer and same loading going through it, the nominal filter will probably only take out 85% of that initial loading instead of the 99.9999999. So if you are going for sterile filtration, or mainly around beer filtration, do stick with the absolute ones. The nominals are fine for what I'd call your nuts and bolts filters, like any sand filters, or just to retain larger particles. But anything to do with filling and sterile filters, make sure you keep with the absolutes. So what some sterile filters might look like, the top one there is the brewology unit. So the left-hand side is the sterile filter, the right-hand side is the pre-filter, and the screen just below it is how they were monitored. So it's quite a good little unit, this one. It had pressure sensors, pre-filters and after filters, and then it automatically kept an eye on the differential pressure going through the filters. On the sterile filter, as soon as you start getting up above 0.2 bar, that's when you really need to start thinking about stopping and cleaning, because if you continually do that, it'll just die very, very quickly. So when we are using the filters, it's a really good idea to monitor and record that differential pressure and see how your filters are performing, because they are quite expensive. It'll help you come up with routines to make the best out of them. Also, as well, when you're changing them, do record the batch numbers and record that you are changing them. It's just really good due diligence to show that you're in control of the process. A bit more of a simple way of looking after them is down on the right-hand side. This was so the one up here was for a keg filler. The one down here is on a small pack line. So you can see we've got 3. So we've got a pre-filter, and then we've got the first 0.45 micron filter, and then we've got a second guard filter down here, just to make sure that if anything failed on this, that the second one would make sure it's taken out. So coming on to the keg, kegs come in generally 3 sizes. The most common now by far is 30 litre and 50 litre. 100 litres kind of been phased out because of manual handling issues. And they're always available in stainless steel and aluminium. More and more these days it is stainless steel. You don't see many aluminium kegs knocking about anymore. They are pressure vessels, so they're generally tested up to 90 psi, and they've got a safe working pressure of 60. They come with several different kinds of spears, so depending on how they're going to be dispensed and what dispensing head they've got, depends on what spear is within them. And what is unique around the stainless steel kegs is that we actually need to reuse it, so we need to make sure it's thoroughly clean. So we've got a few different surfaces that we need to worry about when it comes to that. First of all is the outside of the keg. So we need to clean that up the best we can, get rid of all the old labels and just make it as attractive as what it can to the customer. Although they've probably been stored outside at the back of the pub for 4 weeks underneath a tree getting covered in all sorts, the keg, the landlord doesn't necessarily like getting a dirty keg back. We've got the valve system on the sphere. We obviously need to make sure that as that's broached, everything around it gets cleaned. We've got obviously the inside the sphere, but we've also got outside the sphere. So you can start to see now where there might actually be some shadows around the keg cleaning, because we've suddenly got this long piece in the middle that how we're going to make sure it's all thoroughly cleaned. And then we've obviously got the keg inner surface as well. So before I start using any kegs, the first thing that we're going to check is for damage. So just making sure that it's not dented in any way, the smear's not in a bad way. And we're also going to give it a smell to make sure that it's not got any hydrocarbons in there or paint that we're then going to fill beer and completely destroy. And you might want to just check the spears actually tightened up as well. Generally, when we're cleaning them upside down, and we're going to supply the feeds through the sphere, and we're going to return it through the gas vents. So general stages through what we're going to clean the kegs is we start off with the ullage. So whatever beer's left within the keg, we need to get rid of that. So we can do that by just putting air on top of it and blowing it out. It's also a good thing to remember that that's duty paid beer. So if you can collect that and sample it and make sure it's right, then you can actually claim the duty back on that as well. Then we're going to put a pre-rinse through it. We're basically just going to follow through with a pretty standard CIP now. We're going to put a pre-rinse through, but what we're going to do is pulse it. So we're not just going to put it on for a minute and forget about it. We're going to pulse it as it goes through. And then as we turn the supply off, the flow will actually then come down the sphere and make sure that the whole of the keg's cleaned. After the pre-rinse, put air on top of it, blow it out, and then put a detergent wash on it, again, pulsing. Speak to your chemical manufacturer about what to use around this one. There's a lot of CO2 within a keg. If you use caustic, then you can get a lot of carbonate buildup, and you might think you've got the right caustic strength, but you've not, and you might not actually be cleaning it. Or we can use acid. Once that's over, again, air rinse, air purge to get rid of it, and then water rinse to get rid of all the detergents. Another good thing about having acid is it doesn't take as much rinsing as what caustic does, so you can speed up your stage and also save on water. If you've then got an automatic unit or a steam generator, then you're going to pressurize with steam, let the temperature build up to around about 130, 140 degrees C, leave it there for a minute, and then we're going to put a CO2 purge through it. The other kegs that we've got access to are one-ship kegs. So these get made up from quite a few different plastics these days, and come in some nice sizes as well now, 10, 20, and 30 litres. The main thing about these is the bags. The bags have got a dual layer aluminium lining. That aluminium lining just limits any oxygen pickup and CO2 loss. And then we can see now over a 6-month period, you can see that you're probably the maximum increase you're going to pick up on a 10 or a 20 litre keg is 0.3 ppm, or if you're 30, 0.2 ppm, and then you're going to lose 7% of your CO2 that's in there as well, which the manufacturers will say is comparable to what you'll get in a stainless steel keg. So when it comes to filling the keg, we've got a couple of options. We've got the automatic option, or we've got a manual one. On the automatic one, basically we'll load the keg onto one of the fillers. It could be a rotary filler, it could be a linear filler, or it could be a line filler, or it could be a single head filler. They're filled upside down, like we say, and then now instead of they basically fill through the gas vents. So this just allows nice, slow, controlled fill. Once we've got the gas to the beer to a certain level, we'll then speed up the flow by reducing the back pressure, and then come the end of it, we'll slow it down again. So we'll just, again, just to control the flow. And we know how much is going in there via a flow meter. Now doing this, we can actually fill around about 16 to 80 kegs per hour on a single head filler, like the one on the top right. The same head will also clean, but it'll only clean and fill at around about 18 kegs per hour. So it's the cleaning part of the keg process that makes it very, very takes a lot of time. When you're filling it manually, key kegs are generally done upside down, and there's a special kit that you can get from Key Keg. And then the stainless ones are filled on a slight angle. So this is, if you've got a beer fob like what's on these ones, it'll basically, the flow will automatically stop once this beer fob detects that the beer's full. So the beer will basically lift up a ball that'll cover a hole and it won't fill anymore. So the reason why they're on a little bit of an angle is then when you put them on the floor, there's still headspace within there. If you just filled it without it being on an angle, it'd brim, you'd get hydraulic pressure and you get quite a lot of issues. And yeah, you're probably going to be able to fill between 6 and 8 kegs per hour per head on that. So can filling, cans are quite flimsy and prone to damage. So again, before you come to use them, check them. The flange especially, because you've got problems with the flange, then you're going to might get issues with seaming. And just check the inside layer. They're a lot better these days. In the years gone by, they're like you used to get all sorts of problems with it, but it's fine now. And record the batch numbers. And the same with the ends. There's a little bit of lacquering within the beer contact surface, but they're generally quite sturdy. So when it comes to filling cans, again, we can have a rotary or a linear filler. The rotary fillers are generally for the much larger operations now, so 12,000 to 135,000 containers per hour. Or we can go down to linear ones, which is generally between 4,000 and 6,000 containers per hour. As they come onto the line, they can either be depalletized on an automatic system, or they can come onto some kind of whale tail like what's in the photograph above, where we're just basically picking them up, we're putting them on, and then they'll slide to the conveyor. More and more can lines these days are getting a can wash as well, so they might turn them upside down and then blow air through them or water through them just to make sure there's no contamination dropped into it. The cans have got quite wide lids, and it's quite easy to get something that you don't want in the can before you fill it. As they go onto the filler, they'll go through a CO2 or a nitrogen purge, and that'll basically make it so it's 90% pure within the can. It'll then move over into the filler, and you then just want to control the speed of the fill to make sure that it fobs just nicely. So you've got a nice little dome on the top, and then so you've got the right amount going in. You've got this nice little dome that just pushes out any of the oxygen within the headspace. And there's a few different ways that you can control the level on it. So some come with sensors that'll, when it gets to a certain level, it'll knock off. Some are time. So the time depending on different settings per head, depends on what's going on. And then some of the more expensive ones actually come with a volumetric fill as well. Once they come out of the filler, they might go through a CO2 tunnel, which will just basically put a little kind of layer of CO2 within the can as the lid slides down onto it. The lid will hit the top of the beer foam and then push it out, and the CO2 will just kind of brush the side and just make sure there's no oxygen within there. You do see some as well now that's getting some liquid nitrogen dropped into it, and then the lid's going to go on, and then it'll pass into the seamer. So the seam's really, really important, and it's a double seam that we use. So on the first seam, the end sits on top of the can, and then it basically curls the end onto the flange, and it rolls them flat. And then as it goes on to the second one, that basically just tightens everything up and irons it all out. So there are a few different ways of seeing how the seams worked. We've got some non-destructive tests using X-rays or projectors, really expensive projectors, not that accurate as well. So the standard way of doing it is using tear down, where you basically go into the pack, you'll tear down the actual seam and then measure all these different points and compare that to a standard. So that's something that you can, and your end manufacturer is going to be able to help you out with. As it comes to the seamer, we're going to make sure we check the weight, and we're following the 3 packers rules in the UK for that. We're going to make sure that we give them a water rinse to make sure there's no sticky beer left on there. Then air dry them and then put a date code on. It's also possible to put a date code on at the front, but the main thing is just making sure it goes on when it's dry. And then from that, it's straight on into the packer. Some things to think about while we are filling is if there's any hoses on there that are silicone. Silicone is permeable to oxygen, so oxygen can get in. Filler CIP is dead important because you've got different pipe diameters, and you're really looking for turbulent flow when you're cleaning pipes. So if you've got a pipe that's 1.5 inches down to your filler tubes that are 1/4 inch, something isn't going to get cleaned right. So you need to make sure that there's good chemical use within that, and also the timings are left. You might need soaking time on it rather than just relying on sending it rounds. Oxygen control again. As the fill tubes go up and down, as they're going back down again, they could actually introduce a little bit of oxygen within the can before they start filling. And also really good to keep short distances between the filler and the seamer. We've talked about the CO2 blanket, and again, dialing in the foam levels and fill levels to make sure you've got a really good dome formation for the foam and your fill levels. And if you're going to think about buying an overseas one, especially for the UK, just make sure that they're a lot more expensive and a lot more complex than going out buying a tank or something. So do check the electricity supply is right, and just check for the CE markings as well. At this point as well, this is when we might start noticing that later on in the cycle that we might start getting some foam issues. So we know that using wheat and dextrin malt and high molecular malt torrefied and malted products are going to give us good head retention. But there's also quite a lot through the brewery that we can do. So it's things like keeping an eye on your brewing liquor, making sure you've got calcium levels there. Your pH is spot on all the way through. Your last run-ins, you're not pulling out too many tannins and lipids from your last run-ins. Overuse of kettle finings. Over-foaming. Every time we move beer or foam beer from the kettle onwards, we reduce its ability to keep foam and make foam. Yeast management, making sure the yeast doesn't get too stressed. We can improve heads with hop extracts using Tetra hop. Really does work on heads. PGA as well, really good for head retention. And then in the trade, making sure glasses are clean. CO2 is also something to really keep an eye on. So the temperature, different temperatures as you're serving it, but the CO2 content within the beer as well. If you've not got enough CO2, the CO2 won't grab hold of all them nice proteins and form a head. So make sure them CO2 levels are controlled. And do think about the environment in which you're going to be packaging and storing. So when you're packaging, you want it to be clean and tidy, and everything in order. You want to be able to get materials in and materials out nice and easily without tripping over everybody. You don't want the temperature, massive temperatures in there as well. If you're kegging if you're doing the canning in the brew house next to the hot liquor tank, then it's going to warm up all your beer and you might get filling problems. Moisture levels, again, moisture is probably going to promote lots of lots of mold growth in different areas. And think about as well where you are, no flaking paint on the roof, chemicals usage. You don't want you don't want anything next to the CIP that then the fumes can kind of affect the packages around it. And the same thing with the stores as well. Keep everything nice and tidy. Good temperature control. On high-speed lines especially, poor temperature control can just kill labelling and packing operations as you get different fluctuations in temperature and moisture. So thank you everyone for listening. I hope that was good. I am just going to now try and scoot through what some of the questions are that's coming. So the first one is pasteurization a legal requirement? And what would be the pros and cons of not pasteurizing? So no, it's not a legal requirement. Your requirement is that you serve the best products that you can without harming anyone. So if you put the wrong product into if you put a heavily yeast product into, say, glass container that can't contain any secondary fermentation, can't withhold the pressure of a secondary fermentation, and then that pops, and you've allowed that to happen in the UK, then you're probably going to be in trouble for that. So pros and cons of not pasteurizing. The pros are it does stabilize the shelf life. The cons are it can affect quality. So you do really need to keep an eye on the process as it's going through. What are the best practices for cleaning and keeping sterile filters? Wowzers. So it's always best to speak to your filter supplier on this one. But in my experience, for cleaning, you can get specific chemicals that are perfect for filters that aren't quite as aggressive as what caustic or acid is. So always speak to your filter manufacturer on that one and your chemical supplier, and they'll be able to give you a good use of what's going on. But generally, it's a cold CIP or a warm CIP. One of the most important bits is to make sure that the CIP water is filtered and your CIP tank is filtered as well. So there is the possibility where you could be thinking you're putting fresh water on there, but there's still bits within that water that are going to block your filter. So make sure you're actually filtering to a decent level. You supply CIP water, and when you're operating it, keep a close eye on the differential pressure and don't let it build up too much. If you let it build up, you can go up to about 1.5 bars or 2 bar differential pressure, if I remember rightly. If you let it go and then stop and clean it, you'll just never regenerate it. You've got to make sure you get to a little amount and then clean it, and then you'll get better life out of it. But speak to your filter manufacturer as well about the beer that you're putting through it, because they should be able to help you make it so your filter runs out longer. How often should they be changed? Generally, filters should be changed at least yearly. So that's any filter around the brewery should really get changed every year. It'd be good. I don't know if I've actually know anybody that's managed to keep a sterile filter going for a year, I'll be honest with you. So that'd be interesting to find out. And does dry hopping increase DO2? It can do, yes, depending on how you do it. Yeah, it depends on how you do it. Depends on what DO2 you can pick up. There's so many different methods of doing it. Just opening up a tank door isn't exactly going to let oxygen go in, because there's always generally a layer, especially at the end of a fermenter, there's always a layer of CO2 above it. But then you're kind of breaking that layer as you put it in, and then if you're going to recircuit as well, there's every chance your pump is going to put a little bit of DO2 into it as well. So it's possible. It's something to definitely keep an eye on. So thank you for everyone. Jodie is listening in the background, sending me all the messages. Is there anything else coming? Perfect. Right. Well, thank you very much, everyone. I hope you enjoyed that. Yeah, thanks very much for listening, and we will see you in a couple of weeks' time. Thank you.